This C# script has been developed to demonstrate the binary search algorithm. So the way we demonstrate that is the user will enter an integer value between 1 and 20. The script will then generate an array of n elements with a random integer values between 0 and 20. So if the user enters in the integer value 15, there will be 15 elements within an array, and a random number between 0 and 20 generated in each element of that array. The console will then display the array out to the user and ask the user to enter one of the values listed in the console as a search. So let's say that it displays the array and the value 12 is listed. The user would search for 12. The script will then conduct the binary search for the integer value. If the value cannot be found, the script handles that, exits the while loop, displaying a message that it could not find it. If it does find it, it displays that it found the integer value. So let's demonstrate this script first, and then we'll look at the code. So I'm going to run this script in Visual Studio in debug mode. We're going to enter the value 18, so it's going to build an array with 18 elements, each random element randomly assigning a value between 0 and 20. It's then going to ask me to enter a value that I see here listed to conduct the binary search, so I'm going to enter the value 12. It then looks for 12, and so it first, before it does that, it orders the array, which is a requirement for the binary search algorithm. So these 18 elements are all out of order. It puts them in order and then starts at the middle of the array at 6. And then, as you know, the binary search algorithm, it always cuts the list in half, tests the side that the value could exist in, grabs that and cuts it in half and so forth until it finds the value. So here it found the middle at 6, and then looked here between 6 and 17, found the middle at 11, looked between 11 and 17, and found the value 12, which is the value we were looking for, and displays that in a message. So if you're looking for a value that cannot be found, so I'm going to type 19 here, and let's say the user types 20, that's not in the list. The binary search is conducted, it starts going inward, and then the way I designed this script is it starts pushing back out, it can't find it, and it says, could not locate your integer value in the search, please try again. So let's take a look at this script, and we're just using the system objects, just a console application. We're using nothing more than the simple array data structure, so nothing fancy. I've written the entire program in the main method, so that way, just for simplicity, we could evaluate the code from top to bottom. So right here on line 22, we're just asking the user to enter the value between 1 and 20. I'm using a try catch, so if the user tries to enter something that's not an integer value, it will catch that here in our catch block. I could have further tested to see if the value was between 1 and 20, but for simplicity, I just wanted to immerse myself quickly into the algorithm, the binary search algorithm. So I get what the user has entered. I parse that back out to an integer value. So the very first thing that we need to do here is to populate our array. And so we set up some min and max values that will be randomly assigned to each element within our array. So the minimum value would be 0, the maximum value would be 20, and right here we instantiate the binary search. We call it binary underscore search. That's the name of our array. And we're going to assign right here a random number by doing that, in a loop, we populate each element in our array a random number between the min and max, so between 0 and 20. We assign it in the value of the element of the array, and the elements here, as you see, are essentially gathered by the value that the user inputs. So if the user entered 15, then there would be 15 elements in the array 0 through 14. And so we populate that, and we just write that out to the console right here in line 43, just so we show the user these are the values that were randomly assigned in each element of your array. So now that we've got our array ready to go, one of the requirements of binary search is that we have the array in order. So the very first thing we're going to do is just we've displayed the values in the array out to the user. They're not in order. We ask the user to say, okay, take a look at that array and enter a value that you want this algorithm to search for. So that's what happens here. The user types in, say, 13 because they see 13. So we get that value, and before we conduct the search, right here we have this sort operation that's available to us in an array where we can essentially, as a method, where we can sort the array, and its default behavior is ascending. So it takes all of the elements within the array and conducts a sort. So once it does that, now what we can do is we display that back out to the user just so that they can see, okay, here is the array where elements were randomly generated between 0 and 20, and that array is now in order, so we can conduct our binary search algorithm. So that's all we're doing here, is just displaying that ordered array back out to the user. That's it. So now it moves along and prepares the binary search algorithm, and that's what we have here. Now the binary search algorithm, the way that it works is that, again, given an array or any list of values, it has to locate the middle. And from the middle, it locates the low and it locates the high. And then so from the low and high, after it locates the middle, it then tests a value to see if the low is less than the high. And if it is, it takes a chunk where the value that the user is searching for and verifies, okay, is that the same as the middle? And if it's not, it's going to increment, and you'll see how it manipulates the low and the high. It's going to grab a chunk of that array or a list of sorts, and it's then going to test it, and it has a smaller chunk to work with. And so it constantly takes the array and breaks it in half, and it just keeps going in half and half until it finds the value that the user is looking for. Otherwise, my loop needs to handle that, and you'll see what we do here in a minute. So this is what we declare the low. We start out with the lowest element 0, and then the highest element would be the length of the array. So let's say the user typed in 15 for the length of the array, and then obviously if we subtract 1, that means that the upper subscript element of the array binary underscore search would be 14. So we're looking at elements 0 through 14 to start. And then we locate the middle, which would be the low plus the high divided by 2. Only makes sense. So we calculate the middle. And then we've got this other variable that I added here. This is not a requirement for binary search, but when we're programming, we try to prevent infinite loops. So since we're conducting a while loop, and we're testing to see if a value can be found within the array each time by reducing it in half. If it continues to reduce and it cannot find the integer value, then the loop will just continue in infinity. This is a problem. So I have to keep track, since we know that the binary search algorithm always takes the list and puts it in half. I need to keep track of the middle each time, because what would happen is that the middle would just continue to repeat, and an infinite loop would occur. And so what I'm doing, you'll see inside this while loop, is by keeping track of that, I'm able to eventually actually increment the low and get it larger than the high value so that this loop just jumps out. So essentially, the way that I've written this is that it starts making the array smaller by half, and then if it can't find it, it expands it back out with what it has left, and eventually the low is higher than the high, and then that loop no longer tests to true, and then it says, hey, I can't find it. So that's my way of handling the binary search without going into infinity if it cannot find an integer value. So we go into this loop, and each time we iterate through the loop, we always verify where the middle is. So we take the low and the high and divide by 2, and we get that value that's in the binary underscore search array that's in the middle. So we always do that each time we iterate through. And so each time we iterate through, we run some tests. First of all, we say, okay, is the value that we've got in the middle as we break this list in half, is it the same as what we're looking for? And the value we're looking for is in this variable. And if they match, well, we found our match, and so we've located our integer, and we display that out to the user in the console. And then we have this break here that it jumps out of the loop with that break. All right, now that's if we found it. Well, if we haven't found where they match what the user is looking for, then what happens is we test to see if the middle is greater than what the user is looking for. We also have this, and this is my additional set of code that I'm, again, trying to prevent that infinite loop. And what I'm looking to do is making sure that the middle is not equal to what we're tracking as the middle in the previous loop. So I know that it's not in a loop. So because if it is in a loop, again, it just gets to the middle, it gets to the middle, it gets to the middle, and it never cannot stop getting to the middle. So I make sure that, oh yeah, previously what you thought was the middle is still not the middle. So anyway, as we do that, we redefine the high, and we increment the high. We make sure that it's at least 1 above the middle. So we always need to make sure the high is at least 1 above the middle. And we say, hey, that wasn't a match, so we display that value out to the user. And then again, this is where I'm perpetually tracking, okay, in that last loop, that was the middle, and I put it in track middle, and that's how I do that. So then, eventually what happens, perhaps, is that the middle value, if the middle value is not greater than the value that the user is searching for, then what happens is we have an opportunity to test the low, to define the low. So the low here, we define it as greater than 1. So essentially we're narrowing it down to the middle here. And then we say, hey, okay, during that iteration, then guess what? We didn't find it. So so as we do that, the loop will continue to iterate until it exhausts, and finally the middle is found. So that's really what we're looking for, is we just looking to see that the middle is the same as what the user is looking for. And the idea is we just constantly take what we have in the high and the low, those boundaries, and we cut it in half and go after the middle. So again, this statement below, if for some reason we could not locate the integer value, this tells us that the low is defined at higher than the high, meaning it just kept incrementing and never found the middle. And so we just tell the user, hey, we couldn't locate the integer value in your search, please try again. And then of course this catch block is if the user gives us a value that's other than an integer and it can't be parsed. And so that's our example in C# of writing a console application that demonstrates the binary search algorithm.